Hello, welcome back to data analysis in the humanities. Last time we talked about what a function is, we talked about chaotic functions, we talked about linear and nonlinear functions, and today we are going to talk a little bit about derivatives because you need to understand the basic concept. This is not a mathematics class, right? So don't be scared and don't be afraid of it. We are not going to do mathematics, we are not going to learn how to calculate derivatives and so on. We just want to understand qualitatively what this is about, because as you will see later, some of the machine learning algorithms depend heavily on the idea of derivatives, of finding a local minimum, of climbing up or down a hill, and all these metaphors you can only make sense of if you know what a derivative in principle is doing, right? So let's very briefly have a look at this. So derivatives, if you look here, are the slopes of a function at a particular point. And you can, look at an illustration here perhaps first. So here you have the function we have already plotted before, this nonlinear function. And now you see that at different points at the function, which are these red dots, you have a different slope. The function is sloping in a different way, so that when you are at the bottom of it, there is no slope at all, right? The slope is horizontal, it's just a horizontal line. This is the green line at the bottom, right? And then when you go up, you reach one point, which are the 2 points right and left that come next, at about y equaling 1. And these points have an about 45-degree slope. And then when you go still more up, when you go to 4, for example, on the y-axis, you see that the slope is much steeper. That's perhaps 60 degrees, right? So you see that the slope gets steeper and steeper the higher you go. And so this is the slope at this point. And the derivative is nothing else than a way to calculate how steep is the slope at a particular point of your curve. And so when we look at a hill, let's think of a hill. A hill is essentially the same thing like this function here, but only turned around, right? Flipped on the y-axis, so that the hill, this is not a hill, it's a hole, right? If you want a hill, you have to turn this around. And then you see that when the slope is on a hill, right, when it's positive, when it goes this direction, then you are going up the hill. When it's negative, when you see the hill and it's negative, it goes down, then it goes down, right? So up the hill and down the hill. If the slope is positive, the hill goes up. If the slope is negative, the hill goes down. And if the slope is 0, then you are at the top of the hill. Or also perhaps at the bottom of the hill, right? If the hill comes out of a plane and you're standing on the plane, then again, your slope will be 0, so nothing changes as you walk. And the steepness is what the derivative measures. And why is this important? Because the steepness also tells you how far you are from your goal. Let's say you want to go to the top of the hill, and you have this hill, or you want to go here, let's say at the bottom of this hole, right? At the bottom of this hole. And then the derivative will tell you how far away you are from that, because the steeper it is, the farther away you are. And the more horizontal it is, assuming you are already inside the hole, not sitting on the plane above it, the more horizontal it is, the closer you are to the bottom. And now if you think of this hole as minimizing an error, so you try to guess something, and the closer you come, this children's game where you are looking for something, the other person has hidden something, and the closer you go, they raise the temperature. They tell you it's warmer and warmer and hotter and it's very hot, right? The closer you come to the hidden thing. And so this is like walking along a curve like this. So you are the red dot now, you are trying to find the hidden thing. And when you have reached it, your slope is 0. while when you are far away, your slope is very steep. You make a little step in the right direction and you already see that there is a big difference, right? Now you're much closer. And this is important when we have machine learning algorithms, because in machine learning, you want the program to actually learn something. So you want its guesses to become better over time. This is what machine learning means most of the time. It means the machine is guessing something, is making an informed, statistically informed guess, and the better it guesses, the closer it is to the right answer. And the closer it is, the flatter the slope will be. And so the flatness or steepness of the slope, and this means the derivative of your error function, the function that describes how far away you are, how big your error is from the desired result, the steepness of this derivative is what tells you which way to walk to minimize the error and how much you still have to do to hit the point, to go back to the children's analogy, where the thing is hidden, or to hit the point where the error would be zero. Okay, so this is a very important guidance for learning, for machine learning, because it tells you how much you still have to learn, how far you are, and not only this, it also tells you in which direction you have to walk. Because again, if you see this as an arrow function that tells you how far away you are from the truth, from the right answer, then you know which way to go to find the right answer. Because if you are on the left, let's say on the leftmost red point here, then you see that you just have to follow the negative slope. You have to follow you have to direct your steps towards the point where the slope goes down. And then you will reach eventually the minimum of this function, which is what you want, right? Assuming the minimum is the point of minimum error. And if you are on the right side and you are going up, then you notice while you are going up, your error increases. So that's not good. You need to go back in order again to decrease the error. You need to get in the direction of decreasing error, and this means you need to go in the direction of a negative slope of your derivative, right? And so this is why the derivative is so important. If you just had these original function and not the derivative, it would be just more hard to calculate which direction you want to go, because this function is not linear. So it is arithmetically just more to do to find out where to go. Essentially, of course, you would again be calculating the derivative, but being able to do this with a simple mathematical transformation, you transform this function, you calculate this derivative, and now instead of x squared becomes 2 times x, and now this is a line, and you can just very easily evaluate this line and see where it goes up, where it goes down, and which direction you have to walk, right? So this is the important thing. This is why these derivatives are so important in machine learning. Okay, and how to calculate them? I said it already, right? If you have a function here, you see it in our code. If you have a function that is x squared, then the derivative will be 2x. And how do I know this? Well, this is what mathematics is for. Mathematics tells us the derivative of x squared being 2x, and there are a handful of rules you can use to calculate the derivatives of functions. You can look them up in tables, you can calculate them to some extent. There are some rules how to transform them. So we don't want to worry about this. We are not doing mathematics here, right? So we just assume that there is a way to find the derivative. You can, the easiest for Google it nowadays. So just Google it. And if you have questions about how to do it, consult a mathematics textbook. This is not our point. Our point is to use the derivatives that we are assumed to know in order to understand machine learning, to calculate machine learning. So why is the derivative of x squared equal x times 2? You can kind of understand this if you go step by step, right? So the derivative of a point on a curve tells you the slope of a curve there, how steep the function is, and whether it's going up or down. So for fx equals x squared, the graph is this parabola we already saw, and the slope changes depending on where you are. And why the derivative is 2x, if you pick any point on the curve and say x is 3, the function value at this point of your squaring function will be 9, right? 3 squared. Here we are, so slope at 3, right? You see my value is about 9. It's exactly 9, but we cannot see it so precisely here. And now if I go a little bit to the right and then go to, let's say, 3.2, then I can see my value is a little over 10. And so from these two values now, obviously I can calculate the slope, right? And so if I calculate a slope at this point, then I can find the difference between them, and then I will see that my slope has the formula of 2x. And this is all we need. Yeah, and so this gives you some idea why the slope is like this. But again, we don't need to do this here. We will assume that we have the derivatives of whatever we want to calculate. Okay, the language of calculus now, if you have not done much of that in school, it's built around two ideas. The derivatives describe changes of and rates of slopes, and the integrals describe accumulation areas and totals under a curve. It's the area under a curve, right? And so this is a language for expressing how things vary, how they change over time, and how they build up. And you will find a little more in the lecture notes here about what these words mean. You can also always ask ChatGPT to explain to you. It's actually pretty good at this, but we don't need to do more of this at this point. Okay, so thank you and see you next time. Bye-bye.